Good afternoon, everyone. I'm Michele Merelli, and today I will present you about our recent work in collaboration with Coesia Group and the University of Trento on simulating pouch, flexible pouch with a filling process of non-Newtonian detergent. So we will use two softwares. One of them is Particleworks for the fluid part, and the other one is RecurDyn for the flexible multibody part, to have a coupled simulation where we really integrate information about the fluid and the structure interaction. Thank you for joining us, and today the agenda is the following. First, I will give an introduction on the paper available and the work done, and I will give references to, of course, all the participants of the publication. Then we will also discuss the motivations and why we need this kind of simulation, and what is the so peculiar and particular about it. And then after presenting the softwares, Particleworks and RecurDyn, and the co-simulation that we can achieve by coupling them, I will discuss in detail the flexible pouch filling example that we analyzed with Coesia Group and University of Trento. Moreover, the simulation results will consist in three types of output and type of simulations. One, just to give you already the reference, will analyze the complete formation of the pouch and also filling process with the coupled software. In that, we will analyze different materials of the pouch and the opening to understand how we can maximize the machinery speed, because Coesia develops the machinery that are used to transport and to package this kind of systems. And we will also see in the next slide in more detail what is the pouch and what type of packaging material is that. Then we will also discuss a simulation done in RecurDyn that is about only the formation of the pouch. And at the end, we also see a Particleworks only simulation where we focus on the sloshing phenomena of the detergent inside the pouch while the pouch is moved. At the end, we will also include some conclusions and have a future outlook of what could possibly be done. So let's understand a little bit more about the system. What we present here is as I mentioned, the pouch filling process with a detergent. So flexible stand-up pouches are more and more common in the packaging industry. They can integrate solid, powder, or fluid type of material. And Coesia, as I mentioned, develops the machinery to move them. So the work presented today was performed in collaboration with us by Matteo Berlato. He is now working in the Coesia Group, and he was a former master student at the University of Trento. So the results of his master thesis are presented here. And the work is basically the first commercial application, or one of the first commercial application of the coupling between Particleworks and RecurDyn, when we focus on the flexible, full flex material modeling on the solid, because multibody with fluidodynamics coupling is something that is quite studied and there's already some commercial applications, but the real novelty here is the fact that the pouch is highly flexible and deformable. And RecurDyn can integrate and analyze exactly that with the full flex material method. So in here is the overall simulation, the co-simulation actually. At the beginning, we have the formation of the pouch, so the opening with also some of course, friction model and the forces model by RecurDyn. So in this way, we can analyze the stresses on the pouch and the shape of the pouch. Then the pouch is positioned where the injection of the fluid is. So we have a coupled simulation between Particleworks and RecurDyn, and of course there is a two-way influence between the fluid position and the flexible pouch position. And at the end, after the movement and the sloshing, we have also the closing analysis of the pouch. So this is the process we will analyze. Let's talk about the motivations of why we need to study pouches and why they are increasingly important in the packaging industry. Well, the reason why we see this kind of application, this kind of containers is because they are much more ecological and they have a lower carbon footprint as compared to a rigid PET container, as we can see here in this graphic. But we need to simulate them because they are highly, their behavior and the sloshing and the, let's say, the formation of this kind of highly flexible material is strongly dependent on the material properties and the thickness of the film that forms the pouch. And of course, the flexibility of the pouch increases the complexity of simulating this kind of system, because we will see also example of, let's say, type of PET container like bottles that are not so much flexible or deformable. And this type of simulation was already performed with the coupling between Particleworks and RecurDyn, but really, and the novelty of the approach here is that the pouch is very flexible, and only RecurDyn can study that type of material. So let's understand a little bit more about the software before going into the details and the results. Particleworks is a meshless CFD tool to analyze the fluid dynamic of the system, but with a Lagrangian type of formulation. So instead of having a mesh that we have to compute prior to launching the simulation, as it happens with conventional methodology, we are actually discretizing the fluid automatically with the software at the beginning of the simulation, and the computational nodes are localized where the particles are. So it's a dynamic mesh, a dynamic grid, let's say, that can follow along the fluid field. So because of that, it's very easy to study splash phenomena, jets, and free surface flow. And it doesn't pose all the complexity and difficulties of CAD preparation, but also, as you might expect, we are dealing with flexible solids, so to deal with meshes in this type of realm is very difficult. So it's really a unique approach, the meshless here. And of course, simulation times and the workflow of the simulation in terms of times is reduced because we don't have to deal with, as I mentioned, the CAD cleaning, CAD preparation, and the mesh generation. So this kind of analysis also is feasible not only for academic purposes, but also for commercial type of application with simulation times that are overall in the range of some days max. The conventional application of Particleworks are shown here. We have the automotive sector with sloshing or lubrication of gearboxes or e-motors. We have also piston cooling type of application and let's say grease modeling for bearing lubrication. So we can deal also with the non-Newtonian flows. And in here we have an application that we will see in the coming slide of external, let's say, vehicle contamination or let's say weighting analysis. And this one is actually an example, and we will see it in detail. It's an example of a coupled simulation between RecurDyn and Particleworks. So let's now talk a little bit about RecurDyn. RecurDyn is a multibody simulation software that can work with as a classical multibody dynamic software. So dealing with rigid bodies, the joints, the contact forces, and the constraints of the solids to model like a robotic arm or pistons. But it also integrates the possibility to deal with flexible bodies, as I mentioned. In particular, we will refer to the full flex approach. That is a finite element-like approach. It's a proprietary approach that we can find only with RecurDyn, at least on the commercial side. So this is really the key feature of RecurDyn that distinguishes it from the other multibody solvers. We have a proprietary algorithm for contacts and a library of analytical contacts, because of course the clamping of the pouch was also analyzed in this case. We do have the possibility to do co-simulation with solid-like material in mechatronics environment, but also especially in CFD with Particleworks. So talking about the co-simulation with Particleworks, what we have is an interface and an already built graphic user interface and workflow that was developed by Function Bay and Prometheus Software, the developers of the software. So the integration is already in place, and it's very easy to set up a coupled simulation between RecurDyn and Particleworks, and we can integrate pre and post tools and so on. What it happens is that we have a transfer of loads from MPS, so the moving particle simulation, that is the CFD Particleworks simulation, to the multibody dynamic problem. And the multibody transfer the boundary condition of the walls basically to the MPS problem, so the CFD problem. In terms of numerical solving, the multibody is solved on the GPU, while the fluidodynamics in Particleworks is actually can be computed on the GPU. So we have a coupled simulation that runs both on CPU and GPUs, because as for the CFD one, it's actually very advantageous to work with graphic cards. So in here we have a couple of examples of the coupling where we use only the multibody dynamics feature, not the full flex. You can see here the body of the car is modeled with RecurDyn, while the fluid is modeled with Particleworks. And you can see that there is a clear transfer of forces between the fluid and the solid, lifting the vehicle as it approaches the fluid. You can see here, and all the joints of the car and the contacts are modeled. So we have a better representation of what the weighting would look like. Other type of simulation, we have this kind of gear with a chain. Also in here we have a coupled simulation, so there is an exchange of forces between the fluid and the solid, and it's a two-way coupling. So of course, the dynamic of the chain is well resolved by the multibody, but at the same time, the fluid can influence the position of the chain. And in here we have a, let's say, rigid or not so flexible container that is a PET bottle, analyzing a sloshing type of environment. So the forces of the fluid are transferred to the bottle, and this will result in a small deformation of the bottle, of course, during acceleration or braking. Okay, let's now go in more detail about the study in collaboration with Coesia and University of Trento. So as I mentioned, there are 3 steps of the simulation that we will focus on. We have the opening and the formation of the pouch. We have the filling with the fluid, and then the closing of the pouch. And of course, since this happens at 3 different stages in the machine, we also have the transport of the pouch between the 3 regions. So we really start with the pouch formation, then we move it to the filling place, and then we move it further, as we will see with the videos, to the closing stage. So in terms of numerical difficulties and complexity, as I mentioned, here we are dealing with a coupling that is very complex, because we have large displacement of the pouch, and we deal with that with the multi-flexible body dynamics simulation in RecurDyn. We have non-Newtonian free surface fluid that is very difficult to deal with the conventional CFD tool. And then, of course, we have to couple the 2 methodology in order to have a realistic representation of the system, because a lot of, let's say, a lot of the kinetic energies that is present in the fluid during the injection is dispersed in the deformation of the pouch. So in terms of what we will focus on, here there are a couple of aspects that we wanted to analyze to better understand the behavior of our system while we move it. When we change the opening, so we studied 2 pouches, one with a certain, let's say, opening spacing here, and one with a greater opening space, so a more or less open pouch could result in different flow behaviors, of course. And then also we focused on 2 types of materials, one on the pouch, one that was more M2 and one that was less rigid. Okay, so working on the Young's modulus, we could let's say model 2 types of pouch materials and understand the influence on the pouch behavior. So let's have a look at the simulation results. As I mentioned, we are going to look at 3 types of simulation. One is the full simulation, where we deal with all the stages. One is the design of experiment of the pouch formation, so only the first opening stage is modeled, and it's done in RecurDyn. And at the end, we also focus on the filling and the sloshing of the fluid, and how that can limit the machine speed. So, of course, everything, the final objective here is to analyze and understand what is the maximum machine speed, so we have the higher output in terms of packaging objectives. So let's start to have a look at the simulation results. I have a couple of videos for you. Here we see the entire simulation. We have the pouch formation with clamps. Then we see the pouch moving towards the filling stage. It's clamped, and the fluid starts to be injected in the pouch. You can see the deformation of the pouch. And then it's moved. The sloshing deforms the pouch during movement, and it reaches the final stage where we close the pouch, and we also try to understand if the pouch pouch closing is successful or not, because of course if we have some residues of fluid in the closing region, that will be a failing, let's say, closing. So we have another view here with transparency of the pouch, of the filling part and the sloshing, so you can better appreciate the effect of the fluid on the pouch movement and deformation. You can see here the sloshing, internal sloshing, the deformation of the pouch, some residues that stick on the surface, and then the sloshing on the other side during the deceleration. And at the end, here is the top view, and we see the closing, or partially we see the closing. In terms of pouch formation, so here we are focusing on the first stage. You can see that the outputs are stresses on the pouch and forces, so you can really visualize the final shape, and this is done in RecurDyn only simulation. And you can estimate the time for the pouch formation, and in general you can verify that the pouch forming is successful. In terms of output on the Particleworks side, we can of course visualize every type of observable that is present in conventional CFD: velocity field, pressure field, wetted regions on the pouch. We will see in the next slide. Here is an overview inside Particleworks of the results that we previously saw. And we don't see the pouch in this case because it's transparent, but and from this view it's difficult to see the deformation of the pouch, but yeah, this is the type of output in terms of video that you can expect from Particleworks. Here we have some residues of the fluid that has a little bit of transparency on the pouch. And this is, as I mentioned, the type of output that you can get from the software. Together with the velocity and the pressure, you can understand the number density. So it's a parameter that allows us to understand if there are some air gap inside the fluid region. And in general, it helps us to understand what are the wetted surfaces on the pouch. And then also the kinematic viscosity is something that we can extract and visualize if we are dealing with non-Newtonian fluids. Other type of, let's say, analysis that can be done with this coupling is the analysis of the deformation, defined as lateral deformation of the pouch. So in here, we really see the key results of the simulation that we are discussing. We see the misalignment in the x direction between the barycenter of the pouch and the center of the pouch here, and we can see that for different speed and for different material, for different opening and for different material, we have a different type of misalignment or deformation of the pouch. So this point moves farther away from the center at the bottom. In particular, we see that with a bigger aperture of the pouch, we have higher misalignments. And when we increase, of course, the thickness or the, let's say, the Young modulus, so the stiffness of the pouch, we have lower deformation of the pouch itself. So we can see here, but the effect on the opening is much greater than the effect on the material. Also, there are some second order effects here in terms of behavior for the two opening. So in one case, the misalignment is only in one direction in the, let's say, final phase, while for the more opened configuration, we have a more complex type of behavior. Here is the design of experiment that was performed in a RecurDyn, analyzing the influence of thickness and Young modulus on the pouch formation step. Okay, so this is another type of analysis that was done, and it helps understand where we can move and if we want to reduce, and where we get to if we try to change the Young modulus, the properties of the pouch. So we can see, for instance, that increasing the Young modulus could be problematic due to excessive constraints during the formation. And you can see here that the bottom of the pouch is not correctly formed, but we also know from the previous slide that higher Young modulus could improve the behavior during sloshing. So it's really a trade-off between the fluid movement and the pouch formation here. In terms of sloshing, so the final simulation that was performed, in this case only, with Particleworks, but actually also with RecurDyn, of course, it's still a co-simulation here. We do see the stages of the sloshing. So after the pouch is filled, we start to move it in the right direction, and we can see also from the top view the deformation of the pouch. And at the end, what we want to understand is what is the maximum velocity in the machine while moving the pouch that allow us to later on close the pouch correctly. Because during sloshing, there are two waves here forming on both sides of the pouch. And if they get too high, so if the distance from top is too low, the formation of the, let's say, the sealing is not correctly done. So if we set a distance from top that is, let's say, maximum allowed here, so let's say 5 millimeter, I'm just saying a random number. Of course, we can evaluate what is the effect, in this case, of the opening on the maximum height of the fluid. So in particular here, if we fix this distance, we can see that we can move to higher speeds when the when the pouch is more opened. So again, a trade-off between what we saw previously on the deformation of the pouch and here on the sloshing and the sealing step. So in terms of simulation times and number of particles, I just want to give you a little bit of an overview of how this is positioned, because of course it's important to understand how long this type of simulation can take, and I want to highlight the fact that it was done in a reasonable amount of time, also for let's say R&D workflows that are found usually in the commercial and industrial sector. So as you can see here, we simulate 3 seconds, and the calculation time in hours is in total for the total simulation is 10 hours, so less than 1 day, 1 night basically. The number of particles in the simulation increases, and so also does the step calculation time, because as particles increase, of course, the computational burden of the simulation increases. So we do see that it's not a linear, let's say, a linear step per calculation, sorry, time per simulation step here. So at the beginning, we don't have particles, so only RecurDyn works in the co-simulation, and the step calculation time is very low, so very fast. But then we approach approximately 1 second per simulation step. So just to conclude and to summarize a little bit the main observations that and the results that allowed Coesia Group and the University of Trento to improve their machinery design. So as I mentioned, at the end, we want to focus on the velocity in the machine and the pouch forming steps and the material selection. And in particular, if we want to minimize the deformation of the pouch, we saw that we better work with a slightly less open pouch, because in this way the misalignment between the barycenter and the center is smaller, and also stiffer materials could be better to reduce this type of deformation. On the contrary, we saw that the design of experiment on the pouch formation actually had a limit on the stiffness of the pouch material. When we want instead to focus on the maximization of the machine speed, actually in this case, for the constraint on the distance from top, so the constraint that results from the sealing of the pouch, we can see that a more open pouch is actually suggested, because it allows higher machine speeds, so higher, let's say, filling processes and packaging processes. So what we did was basically to model and to also obtain the first application of the fluid structure interaction simulation between Particleworks and RecurDyn when dealing with full flex, so highly flexible materials on the solid phase. This is a very novel approach. There are only some academic and studies in the field, and we working with the Coesia University of Trento, and also working with engineers that have a great experience in the field here. In this field, we could also validate the methodology and check for the simulation results that were accepted by, as I mentioned, Coesia Group, and this is basically a starting point for further studies. We could analyze different type of fluids. We could analyze different volumes, fluid volumes or pouch volumes. And as we mentioned, this approach proved to be in a reasonable range in terms of simulation times. So we can think about integrating it in the development phase in the industry. I just want to give a little bit of references again if you want to go in more detail on the methodology. First, you can check the EnginSoft newsletter, Autumn 2021 issue, where you have the full paper published in collaboration with Matteo Berlato and Davide Marini, Coesia Group and the University of Trento. And also, I would ask you to follow us on LinkedIn if you want to learn more on Particleworks, and we also have an introductory day on the software, so if you want to register for that, is coming up in more or less 1 week. So with that, I think I'm done with the presentation, and I'm happy to answer your question or your curiosities. Thank you for your attention.